10.2. Projectiles launched at an angle. When a projectile is launched at an angle, there is both a vertical and for vertical we use the letter Y to indicate it, and a horizontal component. Horizontal uses an X. To this projectile's initial velocity. The vector that represents the initial velocity of the projectile is at an angle. And because of this, it can be broken down into its two perpendicular components. We'll call the one in the horizontal direction Vx initial, and one in the y direction Vy initial. Since this projectile is an angle, and the y component is opposite to the angle, the x component is adjacent to the angle, we can figure out the two components by using Vy initial equals Vi sine theta, and Vx initial equals Vi cos theta. There are two possible situations for a projectile launched at an angle. In the first situation, the object comes up and travels right back down to the ground from where it started. This means that it has a vertical displacement of 0. It travels over a horizontal distance, but it doesn't actually change height over the course of its journey. In the second situation, there is a change in height in the vertical direction. This is when a projectile is launched from an angle off a tall surface, like a table, or a countertop, or a cliff. In this case, the displacement in the y direction is equal to negative of the height. Negative because it's down. In either case, you can split up the motion into the two directions. You can solve in the x direction and in the y direction, and you can treat it like two separate problems. You can solve the x direction and the y direction separately. Time is the only variable that links the two sides. Time in the x direction will be the same as time in the y direction. Tx equals Ty, and that's because time is not a vector. Direction doesn't matter to time. Time is the same in all directions. So if you can find time in one direction, you can use it in the other. Here's an example. A projectile is launched from the ground at 25 meters per second at an angle of 15 degrees above the horizontal. How far does it travel? So in this problem, we're looking for dx. That's our unknown. Sometimes in projectile motion, this dx value is referred to as the range of the projectile, or the projectile's maximum range. Quick sketch of the situation is the projectile traveling up in the air and coming back down to the ground height that it started at. We're looking for the horizontal displacement, dx. The vertical displacement is equal to 0 because it goes all the way up and comes back down to the height it started. To solve this problem, we separate it into the two sides, x and y. Remember that on the x direction, the horizontal velocity is constant. So Vx is equal to the initial velocity 25 times cos 15, which is the angle. We're looking for dx, but to solve for it, we need time. To find time, we'll go to the y direction. Vy initial is 25 sine 15. The acceleration in the y direction is negative 9.81 meters per second, and the displacement in the y direction is 0, because it comes to the height it started at. We can use these three pieces of information to solve for time, and once we have time, we can carry it over to the x side to solve for distance. So the first step is to solve for time in the y direction. With the data that we have in the y direction, the most appropriate formula to use is d equals vit plus 1/2 at squared. Because of the double t and t squared, this formula is normally very hard to solve for t. But since displacement equals 0, we're going to put that in right away and get 0 equals vit plus 1/2 at squared. Now, we can divide each term by t to make it easier to solve. T cancels out of the vit term entirely, and the squared goes away from the 1/2 at squared. This leaves us with 0 equals vi plus 1/2 at. Rearranging that, we can get 1/2 at equals negative vi, which gives us t equals 2vi over a, which is 2 times 25 sine 15 divided by 9.81. This gives us a time of 1.3191592 seconds. Remember, don't round your answers until you're done and at the final answer, or you're going to introduce rounding error into your solutions. Next, we use this time we found in the x direction to solve for dx. Since in the x direction we have constant velocity, we can use v equals d over t, which rearranges to give us dx equals vx times t. So dx equals 25 cos 15, which is the vx amount, times the time we found, which is 1.319152, which gives us a dx of 32 meters. Here's another example, this one a little bit harder. A projectile is launched at 50 meters per second at an angle of 60 degrees above the horizontal from a 300-meter cliff. How far away from the cliff does it land? In these problems, it's best to start by drawing a picture. So here's a picture of the situation. We have a cliff that's 300 meters high. The projectile is launched at 60 degrees with a speed of 50 meters per second. It travels up and then continues all the way down to the bottom. The distance we're looking for is the dx, the distance from the base of the cliff. We know the dy, This is the vertical displacement. It falls down 300 meters, so dy equals negative 300 meters. Negative because it falls down. The two different sides of our problem, the x side has Vx equals 50 cos 60, dx equals question mark, and we need time to solve for dx, which is why we go to the y side. Vy initial is 50 sine 60. Acceleration is negative 9.81 because it's falling under the influence of gravity. And the displacement is negative 300 meters because it falls down 300 meters. And we can use this information to find time. Once we have time on the y side, we can use it on the x side to solve for dx. First, we solve for t on the y side. The formula we'd use for the information we have is d equals vit plus 1/2 at squared. But in this case, we have a problem. Displacement, or d, is not 0 this time. It's negative 300. Vi is also not 0 this time. It's shot at an angle. There is some initial velocity. As a result, this formula is too hard to solve for t. It's a quadratic, and you need the quadratic equation to find t. Instead, we're going to solve for Vf, which wasn't one of the things we're looking for, but we can use Vf to find t. The formula we'll use for this is Vf squared equals Vi squared plus 2ad. So Vf equals square root Vi squared plus 2ad. We'll put a negative on this because it's down. We know that the final velocity is going to be down because it's a projectile. It's falling down. Vf equals negative 50 sine 60 squared plus 2 times negative 9.81 times negative 300. Watch for your negatives here. If you lost a negative, it will change your final answer. Vf equals 88.09537 meters per second, and the direction is down. That's what that negative tells us. Next, we use this Vf that we found to solve for t. Now you can solve for t using Vf and another one of the uniform acceleration equations, a equals Vf minus Vi over t, where t equals Vf minus Vi over a once you rearrange it. T equals negative 88.09653 minus initial velocity, which is 50 sine 60, divided by acceleration, which is negative 9.81. This gives us a time equal to 13.8168 seconds. Finally, we can use this time that we found in the y direction in the x direction to solve for dx. Since v equals d over t in the x direction, then dx equals vx times t. Vx is 50 cos 60, and time is 13.8168 seconds. This gives us a horizontal range of 345 meters.